Hello students, and welcome to our next lesson in the complex decision making module. In this lesson, as we mentioned in the previous section, in this lesson we are going to talk about a framework for sequential decision making called Markov Decision Processes. Let's jump right into the definition of a Markov decision process. Throughout this lecture, I will use the acronym or short form for a Markov decision process and refer it to as an MDP. So an MDP is defined as this tuple comprising of four attributes. The first one, S, is the set of states of the problem. A is the set of actions. T is a transition function, which we'll define on the next slides. And R is a reward, which we will define on the upcoming slides. The output of an MDP is a table or a function called a policy. And what the policy does, it takes each state in the state space and outputs a recommended action for that state. Okay. And this policy is usually denoted by P, or most of the times by the Greek letter pi. Let's look at an example in our robot navigation in the 4x3 grid world domain. What are the states in this problem? The states are basically the locations where our agent could be at. And so essentially it's all the cells marked by their column and row position. Okay. One of the cells is the blocked cell, so that should not be part of the state space. What are the actions here? We will assume that our agent can move in the four cardinal directions. So basically we will write them as up, down, left and right, short form shown by the initial letters of each of those actions. Okay. Next up in the set of attributes of MDP is the transition function T. So what the transition function does is it defines how the action transforms the state. In other words, if the agent is at a certain state and it takes a certain action, what would the next state end up being? This can be written in multiple ways. So one way is the transition function. Remember, it's a function, so it should take an input, or it would have some input parameters, and it would output the next state. So one way of specifying the transition function is it takes the current state and the action done at that state, and then it outputs the next state. Another and more conventional and more generic way to specify the transition function is what we have on this slide out here, which is the transition function takes as input three parameters, namely the current state, the action taken at the current state, and then the next state. And it returns a probability of reaching the next state given the state and the action taken at that state. So let's look at an example here. Suppose we say T in our grid world example, T of 1, 1, this is our current state, with the action U. And to the next state 1, 2 is 0.8. So what's that saying in words? It's saying that if the agent is at the current state 1, 1, which is this cell at the bottom left out here, and it does an action U or up, then reaching the cell 1, 2, which is column 1, row 2, which is the cell directly above it, the probability of reaching that cell is 0.8. In other words, if you remember, we had looked at an example where if the agent is trying to do up action at a certain cell, with 80% probability it would go up, but with 10% it would go either left or right. So basically this behavior model of the agent is being encoded through this transition function here. Remember, we have to give the transition function not just at the start state, but we have to give it for every possible state in the state space. Okay. So for example, if I continue with the rest of this model at the start state, then I would write T at 1, 1 and doing action up would end up in 2, 1, which is the cell to the right with probability 0.1. So that's basically encoding the move or go right when trying to do an up action. Remember, the probability here is 0.1, and that's what we are writing here. Okay. And to complete this, we would also write T 1, 1 U ending up in 1, 1 is 0.1, which is it tries to do up, but it ends up going left, hits the wall and stays in 1, 1 with a 10% probability. So this would be the transition function for state 1, 1 for doing action up. If we continue like this, we would have to, as you can understand, we would have to provide first each of the remaining 3 actions at state 1, 1. And corresponding, we would have to write down the next states and what the probabilities are. And then we would have to repeat the same exercise for all the remaining states. And at each state, we would have to give the transition for each of the possible actions, U, D, L, and R. Okay. So in all, our transition function is basically representing the uncertainty in the agent's action. Okay. And as I was saying, similarly, we have to specify T for all the current state action pairs in the problem space. So can you guess, if we specify T for all possible state action pairs, how many entries T is going to have? That's left as an exercise for you. But in this grid world, as you can guess, there are 12 possible states, 4 by 3, 1 less because there's 1 blocked cell, so 11 possible valid states. And in each of those, you can take 4 possible actions. So it's a simple math that you have to do there. Okay. Let's next go on to the last component in the MDP specification, which is the reward function R. R can be specified in multiple ways, 3 ways basically. Either we could associate R with the current state. We denote that by R of S, and that gives, as I said, reward at state S. The second option is to denote reward as reward associated with a state and an action taken at that state. So this is to be given for every state action pair. Finally, we could specify the reward just as we did the transition function, which is we take the current state, the current action, and the next state, and then we specify the reward for that. In other words, we specify the reward as doing action A at state S and going to next state S prime. As you can see, the number of entries of the reward function increases as we go from the first option to the third option, because essentially we're looking at more entries as we go down this row. So in our robot grid world environment that we have been looking at till now, we will use the simplest form, which is reward associated with a certain state. And basically we will say that at the non-goal state and non-avoid state, so any of the intermediate states, the reward for reaching that state would be negative 0.04. And for the goal state at location column 4 row 3, it's +1, and for the avoid state the reward is -1. And you can interpret this negative 0.04 as kind of telling the robot that don't linger on or don't loiter on in non-terminal states. So if it accrues a negative reward for non-terminal states, that would say that staying in the non-terminal states is bad for it utility-wise, and so it will be motivated to go towards, to get out of the non-terminal states and hopefully go towards the goal state. If not, if it's unlucky or does some miscalculation, then it would end up in the avoid state. But basically, don't stay in the non-terminal state is signified by a small negative reward. Now, the transition function that we have defined, we could also denote that in the form of a search tree. Here's an example. Suppose the agent is starting at state S at the bottom left corner. Then it can take 4 actions, and let's say it takes a certain actions. I call it A here. It could be up, down, left, right, and so it ends up with a certain state action pair. And with that state action pair, it would have a possibility to go to different, as we saw, either the cell above or to the cell to its right, or hit the wall and remain in the current state. So basically 3 possible states. And so then you would have each of those 3 possible states as 3 triangles here, and from each of those you would continue again with the arrows. So basically I can denote the transition function as a search tree, and as you can notice in this search tree I've used the convention that a state corresponds to a triangle, a blue triangle, and a state action pair corresponds to a green circle. Okay. Now, we had talked about rewards a few slides ago, reward associated with states or state action and state action, next state, and so on. Let's now tie rewards to the utility. So if you remember, the idea of a utility-based agent's idea was that at each state, it was trying to select the action that would give it the maximum expected utility. This was what we learned in the simple decision-making module. We will have the same idea in this module as well, just instead of having a single step decision as we had in the single decision making case, here the agent has to select this action, make the decision of selecting the action at every step that it reaches. in our grid world domain, the agent have to select this action, whether it wants to do up, down, left, or right at each cell that it reaches. Now let's tie rewards, what we had defined in the MDP, to utilities. So utilities are based on rewards, and basically there are two ways to define utilities from rewards. Okay, let's look at them. Okay, so basically as the agent is going through different steps, you can understand that it's getting a reward at each state. In our grid world environment, for each non-terminal state that it reaches, we said that it would get a reward of negative 0.04. Let's look at an example here. Let's suppose our agent out here shown by a robot like R2D2, it has two choices, which is it could either take the path to its left, and it has 4 diamonds along its path, and it picks one of them at each step. Diamonds are like rewards. Or its other option is to go right, and then it does not get anything initially, but then it gets all the 4 diamonds or the entire reward together at the last state. So the agent faces definitely choices here, or it has to make decisions. Does it want more or less? Upfront it wants more, or upfront it wants less, and then large reward at the end. So here we are saying whether it wants, suppose it's 3 step, like 3 actions. Does it want to go like 1 and then get a reward of 2 and followed by reward of 2, or does it want to choose like 2 followed by 3, reward of 2, reward of 3, reward of 4? Clearly this option is larger. Now or later, as we see in this diagram out here, first 2 steps it does not get anything. In the 3rd step it gets a reward of 1, or whether it wants right away it wants a reward, and so that it does not get reward in subsequent steps. Okay. Another thing that we consider, inspired by real life, is when we are looking at sequences and rewards at each step of the sequences, rewards over sequences. Because I'm looking into the future and trying to estimate future rewards, I assume that the reward that I'm getting at like a step that is further away is not the exact reward that I will get. So basically, because it's happening in the future and things might change in the future, so I will not take the reward at its face value. I will rather decrement the reward a bit. Decrement to account for the fact that in the future things might change and I might not get that reward after all. I might not get the full reward after all. Okay. This also takes care of the fact that it allows the agent to prefer rewards now than to prefer rewards later. So here's an example here. If I have a reward which is worth now, if I delay the reward, I don't take it now and I take it in the next step, then its value would decrement by a certain fraction. I denote that fraction by gamma. Okay. And then if I take it 2 steps away, it would decrement by gamma square. So basically, if I take the reward like many steps away, as you can guess, because gamma will be a fraction between 0 and 1. So basically, gamma squared becomes smaller, gamma to the power of k is even smaller, which means that if I'm looking at a reward of 1 now, if I wait, let's say, for 100 steps, then the reward will be worth nothing. Okay, so this makes rewards decay. So the way we decay these rewards is by associating a discount factor that I showed, so that we saw on the previous slide. So each time a robot takes a step, or we say descend a level in the search tree, we multiply the discount, but multiply the reward by the discount factor once. Okay, so basically at the first step it will have 1, in the second step it will have gamma, 3rd step it will have gamma square, and like that gamma to the power of k in the k plus 1th step. Okay. There are 2 advantages of this. One is to model real life situations where something is worth more now and is worth less in the future. Also, this discount factor helps algorithms converge. As we will see, the MDP algorithms, it helps them converge. So one example factor could be discount factor of 0.5. So as you can guess, 0.1 here, 0.5 here, 0.25 here, and then as you go downwards, the reward decreases further and further. This is the math showing what the reward would be. If I get a reward of 1 in the first step, 2 in the second step, and 3 in the third step. Okay, so clearly U of going in the order 1, 2, 3 is less than the utility. If I first take the reward 3 action, then the reward 2 action, and the reward 1 action. Okay. There's a theorem called stationary preferences that allows us to define utilities, which says that if I have two preferences over sequential steps, the first is A1, A2, A3 all the way up to AN, and then I have B1, B2, B3 all the way up to BN. And so if I have the preference set A1, A2 is more preferred than the set B1, B2, the actions B1, B2, then if I prepend this with a reward, then given that I am prepending both with the same reward, this still the A preferences still dominate or still are better than the B preferences. Okay, so basically what this is saying is prepending a reward does not change the preferences of subsequent states. So given this, given the preferences are not changing, that is adding a reward is still keeping the relative order among the future states the same, relative order of preferences between the future states the same. There are two ways to define utilities. One is additive utility, which is if you have rewards at subsequent steps R0, R1, R2, and so on, you just add them. The other is discounted utility, which is again you add them, but at subsequent steps, like we said, you discount the reward with a factor gamma to the power of k, where k is the k plus 1, the step number. At k plus 1 step, you would discount it by gamma to the power of k, where gamma is a fraction between 0 and 1. If we go to infinity, what happens? Well, reward keeps getting smaller and smaller, and ultimately it converges. And so basically it will converge to the value of R max, which is the maximum reward, the first step reward, over 1 minus gamma, where gamma is the discount factor. As you can guess, if gamma is very close to 1, then this works out to be 0, and so then as we wait more and more, so then the factor increases. A smaller gamma means a smaller horizon, short-term focus. Okay, and there's also an absorbing state, which is if we go to the infinite horizon, that guarantees that every policy for terminal state will eventually be reached. Let's look at another example beside our grid world navigation, and this is a car racing example. So the problem specifies that a car has to go from a start state to a goal state while racing. Okay, racing by itself. Okay, maybe its objective is to go there in the quickest possible time. Okay, so now the states are shown by this. That the car can be in 3 states: cool, shown by blue; warm, shown by red; and overheated, shown by gray. If it's overheated, then it's broken down, it cannot work anymore. Okay. Now, the car has 2 actions, going slow and going fast. The transitions through the different states for the different actions is given by this transition function shown by this picture. So as you can see out here, if it's in a cool state and it keeps going slow, takes the action slow, then it remains in the cool state. If it tries to go fast in this state, then with 50% probability it will still remain in cool state, but with 50% probability it will end up in the warm state. Similar transitions are given from the warm state as well. And then from the overheated state, the car is done. So basically there are no transitions out of this. And then associated with each of the state action pairs, you can see that there's a reward associated with each of these. Okay, let's first try to draw this in the form of and there's also a reward function, and one thing of the reward function is if it goes fast, it gets double the reward, which signifies that it's getting to the goal faster. As I said, let's try to draw this as a search tree. So initially, we suppose that the car is in the cool state. So at the cool state, it can go either fast or slow, shown by the purple action and the red action. Okay. So then if it takes this action, if it takes the slow action, then it will end up in the cool state. Remember, the transition function says that if you're at cool and going slow, you will still remain in the cool state. So that's what we're showing out here. On the other hand, if it went fast, then with 50% chance it would end up cool and 50% chance it would end up fast. Okay, and like this we continue in the search tree. So basically at the cool state, again we have if it goes slow, then it remains in cool. If it goes fast, it could be 50-50 chance between these two. And then the same thing here, but in the fast state, if it goes slow, then it will again end up either 50% times cool, 50% times in the heated state. Whereas if it keeps going fast still in this state, then it will end up overheated. Okay, this is not the end of the tree, because see here we still have certain cool states, and given that it's not reached the goal, the car will have to continue like this. So basically this is what the tree will look like. When will this end? Well, when it reaches the goal state. We do not know how many time steps there are in the goal state, because remember, it's all utility driven. Okay, so basically this is what the search tree would look like. But if we try to solve this as a search tree, like we are given this tree and we try to find the path through this that gives you the maximum utility, then that is very problematic. Okay, because remember, unlike the search algorithms, there is no goal state here. What you have is you have the rewards that are accruing as you take each of the state action pairs. And finally, when you get to the end of the track, when you get to the end of the set of steps that you have to take, you will have a certain reward. So basically what you have to do is you will have to search. Your search algorithm will have to search through each path in this tree and then locate the path that gives it the highest sum of rewards. And remember, sum of rewards meaning I'm meaning utilities here, which is discounted sum of rewards. But if we want to do this with a search algorithm, this will be too much work, because states are repeated and we only need to compute quantities once. And the tree can go, if the goal state is very far, if the end of the track is very far for the racing car, tree can go on forever. If we do a depth limited computation but with increased depths, then until the change is small, that would work. But the deep parts of the tree don't matter if gamma is less than 1. So basically search tree is not very efficient in this case. So that's why we have to use Markov decision processes in this scenario. We will look at how Markov decision processes solves this problem in our next section. For the time being, let's just wrap up this lecture by reminding what the definition of an MDP was. Remember, there were 4 attributes in it: state space, action space, transition function, and reward function. We looked at the state and action space, which were not very difficult to specify. Then we said what the transition function was, and we also said what the reward function was. So till now we have looked at 2 quantities related to MDPs. Policy, we said, was the output, which was a mapping from each state in the state space to a possible action that would be taken at that state that would ensure maximum expected utility over the sequence of steps that the agent takes. And we also talked about utility, which we defined as sum of discounted rewards. In our next lesson, we will look at how to find the policy from the parameters, the inputs, state, action, transition function, and rewards, the 4 inputs of the MDP. We'll look at an algorithm called value iteration algorithm to solve that.